All right, 2020 practice problem. This is number 2, a circuit question, and they've given us a very straightforward circuit here with an ideal part of a battery and the approximation of the real part by saying let's have an internal resistance, and then we connect it to an external resistor that we can actually pick up off the shelf. Now here's the thing, inside this dotted box is a battery, and you cannot access directly the two parts that are inside of it, the ideal part and the internal resistance part. In real life, these are all sort of mixed together. So you cannot do this, for example, because that would be to separate the internal resistance from the ideal part of the battery, and you would be stabbing the battery with your voltmeter, because this dotted box here is the actual physical boundary of the battery. So we can stick a voltmeter over here because these are wires. These are actual wires that are connecting the positive side of the battery to a resistor and the negative side of the battery to the resistor. And we can stick an ammeter in the middle here. Just separate out a wire on this side and a wire on that side. We cannot do that inside this box. So keep that in mind as we go through this. So what we want to do is figure out the internal resistance. The students are expected to find the internal resistance by plotting their data in a graph. This is an indication that we need to come up with a way of getting multiple data points, not just one. What are we allowed to change? We're not allowed to change the voltage, the ideal part. We're not allowed to change the internal resistance. We are only allowed to change the external resistor, and the effect that that is going to have is that it will change the voltage across the internal resistor, the external resistor. It will also change the current through the system. They did also tell us that we have access to a variety of resistors. So if we take a look at this system here, we're going to have Kirchhoff's loop rule, and then we will have the ideal part. Keep in mind that we cannot access the real part directly. We have the internal resistance that also we cannot access that directly. And then we have the external resistance, which we can access directly, and that will be equal to 0. So these two guys are in series. They will have the same current through them. And we can rearrange our equation like this. Now keep in mind, we cannot access this E. We cannot access the ideal part directly. So we can figure out what the total current is through the system algebraically, but we can't be any more specific than this yet because we don't know E and we don't know little r, even though we can measure I directly and we can measure R directly with our multimeters. Did they said that? Yeah, multimeters. So we can measure the resistance directly with multimeters. Now we can also measure the voltage directly as well as calculate it. So we can come up with an equation here. Notice how I've gotten rid of the current. We can come up with an equation here with two things that we can measure directly. We can measure the voltage directly and we can measure the resistance directly. And unfortunately, we have the resistance in two spots here. So how about we flip everything upside down? If we flip everything upside down, and then we have R plus R over E, and then 1 over R. And oh, we still have this in two places. Let's clean this up and multiply this guy through. So we're going to have 1 over VR is going to be, let's see here, this is going to be R over E, and then 1 over R. And then we do the same thing with the other guy, plus this will be big R over big R and leaves just with 1 over E. All right, Now, let's see here. What are we measuring directly is we can measure this guy directly, and we can measure this guy directly. And we can choose the R. So I would make that guy be the X, which would make this guy the Y. So you choose the resistance, and then you measure the effect of that new resistor on the voltage across that resistor. And then we're going to have slope and y-intercept. If you did the 2015 test, you should notice that this is the same exact equation as they had in the 2015 test that they had you graph. They gave you the data for it and they said, here, graph it, and then find these things. So our y-intercept is going to be the ideal part, and then we can use that as part of the slope to get the internal resistance. But what are we measuring? What are we changing? And what equipment do we need? Now that I've done all this theoretical setup, I can say for part A, and it might help if I actually give myself space by moving these things. Maybe all that stuff. Oh, I lost the M. There we go. Okay, so if we move those guys up. Okay, so for part A, we're going to clearly identify the quantities to be measured. Resistance of R with ohm meter, which is going to be part of the multimeter, and voltage across R with voltmeter. Notice how we don't actually need, notice how I got rid of the current. We don't actually need an ammeter. You could do that, but the trouble that you're going to have is when you change this R, you're going to also be changing that R. So if you're measuring the current, your slope itself would be changing. That's not going to work real well. We need a way of getting a straight line. So for part B, describe the procedure. Okay, so what I need is a list of instructions, and this set of equations is not the procedure. It's not an experimental procedure. It is a theoretical derivation starting from Kirchhoff's loop rule and ending up with a usable equation for this situation. So what we need is a procedure. So 1, choose a resistor and measure resistance with multimeter. Running out of space there, so I won't bother with that. Okay, number 2, connect resistor to circuit and measure voltage across it, VR, with voltmeter. Three, repeat steps 1 and 2 for at least 5 resistors. 4, keep wires the same. So what we're doing is change only the resistor. Oh yes, and I should say the voltage of that resistor is VR because I use this later on here in part B. All right, scrolling down to get to part C. All right, C, which quantities, raw data, would be graphed to produce a graph from which we can get the internal resistance. Okay, so that's why I did this theoretical work up here first. I have my equation that I'm testing out. So for part C, what I'm going to choose is I'm going to graph on the x-axis 1 over r, and on the y-axis I'm going to graph 1 over the voltage. So I'm going to need to get rid of some of these things, and you need to go also. So for part C, what I would write is, use this equation here, C, x-axis, I would graph 1 over r, y-axis, I would graph 1 over VR. And then for part D, which information from the graph would actually get us internal resistance? Okay, so step 1, y-intercept is ideal voltage of battery. 2, slope of line graphed is R over E. So R equals y-intercept times slope, because the y-intercept is, oh wait a second, no, the y-intercept is 1 over E. 1 over E. All right. So that will change this just a little bit. So R equals slope times E, which is the same thing as saying, well, since E is going to be 1 over here, we're going to have, that'll be the same thing as slope divided by y-intercept. All right, part E. After we do everything, then we say, oh no, we made a mistake, and we didn't account for the resistance of the wires. What's that going to do? Okay, the resistance of the wires. I need some more space here, so you got to go. And now I'm regretting erasing all of my theoretical analysis from up above, because that will be useful to look at. Because what it means is the total resistance is split up a little bit differently than we originally wrote down. So let's relook at that briefly. So for part E, V of, wait a second, this will be ideal part, internal resistance part, known resistor part, and now what they're telling us is that we should have had also the wire. So we measured this guy, we knew that guy, we didn't account for this. So what this guy is going to do is take away from the internal resistance. So it's going to take away from the internal resistance. It's going to say the internal resistance is actually smaller than what we thought it was. So actual R is smaller than the calculated R. And this is because sum of voltage is from wires and not from the internal resistance. All right, I hope you notice how this is a very verbal explanation of how to do this problem, as opposed to the symbolic and graphical representation that was in the 2015 number 2. So if you take a look at that, you take a look at this, it's the same problem, but it's a different way of presenting the solution.